Hello everyone, this is the third video of the channel, and if you're new, welcome. If you're just here to solve the problem, welcome as well. So today we're just going to go over another example that's similar to those previous two, but this time just with a distributed load, okay? So the process is actually very simple, so let's just jump right into it, all right? And of course, as always, the question is just asking, find the reactions at A and C okay? So first step, always to identify what reactions are we looking for, right? So we can see that there is a roller support at A, so that is resisting the force at A, so AY, right? And then C is also resisting, but this is a hinge support, so it is resisting CY and CX, all right? So this is covered in the previous video, so if you want to check it out for more details, I'd highly recommend so if you haven't gotten this point yet, okay? So we're gonna go pretty fast, all right? So once we have these, we've identified what kind of reactions there are, the next thing would just be to solve the problem, all right? Now, to solve this problem, you need to understand how distributed loads work. And basically, whenever you see a distributed load, it's actually very hard to calculate. So what you actually just do is just replace distributed load. So replace distributed load with an equivalent excuse the spelling, a point load, okay? So what this means is basically, you'll see, okay? So right now, this might look kind of funky, being the 5 and the 2 here, but what that essentially is just a combined load. So you can think about it as a triangular load going like this and a rectangular load, all right? Now what are the magnitudes of this? Well, the rectangular loads, as you can see here, are just 2 kilonewtons per meter, right? So 2 kilonewtons per meters. And sorry about this, I actually forgot to add in the dimensions real quick, so let me just do that right now. All right, so from the end of the beam to A is 6 meters, followed by 4 meters. We'll shift this over, and this is actually 8 meters. Okay, perfect. So this distributed load that we're looking at here, right, is actually a combination of a triangular load and a rectangular load, all right? Now, just to break this up, it's pretty intuitive that if this is just 5 kilonewtons, this is just 2 kilonewtons, the magnitude on the rectangular would be 2 kilonewtons, and the triangular would be 3 kilonewtons per meter. That's coming from just 5 minus 2, right? So once we have that split it up, it's now really easy to calculate the equivalent point load, right? So to give you a basic theory on this, I mean, when you're applying this rectangular load, right, the equivalent point load would just be the length that this distributed load is acting on, and then that would just be the total amount, like the total amount of force that's being applied on, let's say, this beam, right? And then where you place that load is just intuitively speaking, just say for an example, intuitively speaking, this would just be at the center because it's a rectangle, right? It's acting evenly, right? It'd just be at the center. So what is this length now? So this is just this length because it is acting here on this beam, right? From B to C, right? So this would be 10 meters, And this force, equivalent force, would be just 2 kilonewtons times 10, which is just 20 kilonewtons total, right? And it is acting at the middle of the beam, okay? So, what about this triangular load? Well, same thing. The distance here is 10, right? 10 meters. And this 3 kilonewtons per meter, right? As you probably know, the area of a triangle is base times height divided by 2. So that's 3 times 10 divided by 2, or times by a half, right? And you would get 15 kilonewtons total, right? So that's just the total amount of force that's acting on here, okay, on this beam. So in other words, now let me just ask you a question. Where do you think that the point load should be placed, right? Do you think it's smack dab in the middle, just like the rectangle? Or maybe it's on this side? Or maybe it's somewhere, you know, here, because you think that this bit is bigger than this bit, you know, where would you place it? Well, the answer is here, right? Somewhere here. We know because, you know, if you place the load, this side would just simply be heavier than this side, right? So it'd be somewhere here. And what is that distance? Well, it is 2/3 of the length, all right? 2/3 of the length starting from the smaller end, or vice versa, 1/3 starting from here, from the larger end, all right? So 1/3 of 10, right, is just 10/3. Or you can do 20/3 on this side, right? So this load, this equivalent load, would be 15 kilonewtons, the total load, at 1/3 of 10, starting from the larger end, okay? So once you have this, it is actually pretty simple now, right? You can, in this case, I'll just copy it down here, but feel free to, you know, redraw it or draw it on the same thing. But instead of this complicated distributed load that nobody wants to calculate, right, you have acting on the beam instead. We broke this down, so that's from the triangle, it's 15 kilonewtons here, and 20 kilonewtons here. Once again, this 15 is from the triangle, and this one is from the rectangle, okay? Hope that makes sense. And the distances are very important, so we'll mark those down, all right? So this is 5 meters, right to here, right in the center, all right? And this one is from here to here. The end would be 20/3, and that's just, once again, this distance you see here, okay? So once you have that down, it is all the same steps from before, all right? Using your 3 equations, let's just solve this, all right? First step I would do, I would just find AY by taking the sum of moments around CY, okay? And I don't think I mentioned this in previous videos, but the reason why I'm choosing CY and not AY is because simply if you place like a sort of, I guess, center of rotation there, it eliminates the need to find both CY and CX, whereas if you placed it, let's say here, you would still need to account for CX being part of something that rotates the entire beam or truss or whatever you want to call it, okay? So let's just do sum of moments around C. Once again, counterclockwise equals positive, and the whole thing isn't spinning into space, so it's equal to 0. All right, so that would just be, let's do the 20 kilonewtons first. All right, so 20 kilonewtons, and we can see that it's causing the thing to spin counterclockwise, so it's positive, times 5 meters. Okay, and that's just the distance from C, 5 meters. Okay. So 20 times 5 plus the second load, which is 15 kilonewtons, times 20 over 3, which is the distance. And then, finally, we have to account for AY. Now, which way is AY spinning it? It will most likely spin it this way, which is clockwise. So it's negative AY times, now what's the distance to C? That's perpendicular to the force. It's 4 meters, okay? Don't get confused by any diagonals or anything you have to consider like that. Just always remember it is the perpendicular distance to the force, in which the force is acting on, excuse me. So that's 4, and then that equals 0. Now this becomes a very simple equation then. So we can just find AY, okay? So that's 20 times 5 equals 100 plus 15 times 20 over 3. So 15 times 20 over 3 would equal to 100, and then equals 4AY. So that's 200 divided by 4, and that's AY equals 50 kilonewtons, okay? So once you have that, you can just say AY equals 50 kilonewtons and move on with the next step, which is just the sum of forces in both the y direction and the x direction. Let's start with the y direction. Set upwards equals positive, and we just find all the forces acting. So that's 15 going downwards, right? So negative 15 minus 20 going down, right? So 20, and then plus AY equals 50, so 50 kilonewtons, and then finally plus CY equals 0. All right, that's all the forces going up and down. Add it all together, it's 0, okay? Because nothing is moving, all right? So that's, 50 minus 35, right, equals negative CY. So CY is then equal just to negative 15 kilonewtons, all right? So which just means that if we defined CY going upwards here, it would just be going downwards instead, okay? So, and then you might have noticed that I'm missing CX. Well, CX, if you just look at it intuitively, right? Well, you don't have to write this down, but it's always good practice to do so, right? CX is just equal 0. Why? Because there's nothing acting horizontally, right? Again, don't get confused by this diagonal or anything like that. We've already broken down what needs to be broken down into horizontal and vertical. And let's say you had like a diagonal force here, right? It would be a bit harder of a problem, but same principle. If you just want to you would just want to kind of just break that out into horizontal and vertical components, all right? So CX would just equal 0. So once again, to summarize, let's just summarize here. Why don't I just copy the original problem? Okay. So let's just copy that, move that down here, all right? And we found our answers to be CY equals negative 15. That is a very small highlighter. CY equals negative 15, AY equals 50, CX equals 0. All right, so let's just mark that down real quick. All right, so no CX, AY equals 50 kilonewtons, and CY equals negative 15 kilonewtons. All right, and that's just simply your problem, all right? CX equals 0 again, so I didn't put it down. So I guess if you want to do a final check as good practice, you can always make sure that it makes sense intuitively, right? So imagine you're placing some sort of irregular load, right? If you place that, this whole thing would want to probably spin this way, right? Same thing if you have like something here and then you're placing something here, right? Like a big block, right? It would want to spin probably this way, right? So in order to do that, I guess something has to be pushing up, something has to be pulling it back down if something is pulling it up, right? And it just has to not spin this way. So that's just how A and C react to this load, and these values are just what it has to be in order for it to resist it moving in any of the three directions. All right, so that's all for today's problem, but I hope that makes sense. If you have any questions, please leave it in the comments below. I'll be loosely following them, so let me know if it helped you. That's great. And if you're cramming in for an exam, I know how that feels, so good luck with those. All right, but until then, that's it. I'll see you in the next video. Goodbye.